If you want to run a fixed workload for a fixed number of subintervals, all you need is warm-up seconds and measure seconds and subinterval seconds. Otherwise, we need to specify the focus metric. The focus metric is what we are making a valid measurement of using measure, the seen enough and stop feature. Also, when we're adjusting the total IOPS using the PID loop dynamic feedback control, df equals PID functionality, the focus metric is the feedback in the dynamic feedback control loop. What we specify is the focus rollup. The focus metric is evaluated at the granularity of the focus rollup. If you're using the default focus rollup, which is all, there's only one instance, and therefore measurement or dynamic feedback control will happen for all of the workloads threads together in unison. When a focus rollup is used that has multiple rollup instances, in a successful test step, the same subinterval sequence in each rollup instance will need to meet separately the measurement criteria. And when dynamic feedback control equals PID is used, DFC equals PID, we do that dynamic feedback control at the granularity of the individual rollup instance, which in this case would be separately for each port. The source of the focus metric can either be from host workload data, that is to say, data that's sent by the IV workload threads on the test hosts, and we always have that data. Or you can say source equals RAID subsystem, and this means that we're going to be selecting the focus metric from real-time performance data collected from a command device. And in that case, there's a small list of subsystem metrics for specific subsystem resource types, such as port, for example, which are in an IV source code table that specifies which of the raw RM Live API data should be filtered and rolled up at the end of every subinterval by rollup instance. And it's from those RM Live API metrics which are filtered by rollup instance and rolled up by rollup instance. Those are the ones that you can select from to do dynamic feedback control on. When you're selecting source equals workload, there's three sub-parameters that you have to specify: category, accumulator type, and accessor. And in order to explain these, it's easier to explain first accessor, then category, then accumulator type. An accumulator is something that you push numbers into in order to be able to compute summary values. And we use this mechanism to record the service times of individual IOs. So every time that an IO completes, IV posts that service time into one of a row of buckets of accumulators for service time. So as every IO completes, the service time for that IO gets posted into one accumulator out of a matrix of accumulators, and we'll explain that in a minute. But first, about accumulators themselves. The selectable values for accessor are the names of the methods that you can use to retrieve something from an accumulator. And when you specify average, you get the average value, in this case of service time or whatever else that it was that you're pushing into the accumulator. The count is the number of times something has been pushed in. The min max are the min and max of the service time or whatever. And then you have the sum of all service times put in so far, and then you can also get the variance and standard deviation. Individual IOs, you can tell if it's a read or write by the command. You can see the block size. You can see the logical block address that it goes to. You get a service time for that IO. And in IV, the service time is the duration from just before IV launched the IO using the AIO interface, including some possible latency within AIO if there's not an available underlying OS device driver tag, until IV received the notification that the IO was complete. And this is very accurate timing to nanosecond resolution and with very low CPU busy, so this timing is accurate. I may think of changing the definition of service time instead of being from when the beginning of the IV C++ statement that was trying to launch the IO to when the IO completes. Instead of that, perhaps defining it as from the moment that the C++ call to launch the IO returned, indicating that an underlying OS tag had been obtained and that the IO had been launched from that point to the end of the subinterval. If you're not running at IOPS equals max, then it makes sense to talk about in IV what we call the response time. And that's the time from the IO sequencer scheduled start time of an IO until the time that the IO is complete. This includes waiting an IV until there's a thread available within the number of max tags. IV keeps track of how many active IOs it has running for a particular workload thread on a particular LUN. The maximum limit for that is specified by the max tags parameter. So if IV already has all of its tags in use and the scheduled time happens, then you'll wait. There'll be a waiting period while you're waiting to have an available IV tag. And so that's analogous to the application level response time. When you're running at IOPS equals max, all IOs have a scheduled start time of 0, and so it doesn't calculate response time because it's not meaningful in that case. When an IO completes, IV posts the service time into a particular bucket. And there's a lookup for the buckets, so there's one set of buckets for reads, another set of buckets for writes, and then within the buckets that are for reads, there's a group that are for random, there's a group for sequential, and it's the IO sequencer itself which announces whether it's a random or a sequential sequencer. And then within, for example, the read random group or within the write sequential group, etc., within each of those, there's a further breakdown by service time as a histogram of the service time. So in the first millisecond is broken up into 10 buckets by 1/10 of a millisecond. Then you have 1 millisecond wide buckets from 1 millisecond service time up to 20 millisecond service time. Then you've got 10 milliseconds wide buckets up to 100 milliseconds. And then you got 100 millisecond wide buckets up to 1 second, and then you got 1 second buckets up to like 5 seconds. The IV engine rollup mechanism operates on a view of the categories as an array, and the breakdowns within that array by read or write, by random or sequential, in this case by service time, those are a layer of interpretation that's put on by the IV workload thread as it posts into the array, and then and then that complete breakdown by all of those buckets is carried through all rollups all the way up. So you always have all of those breakdowns. But instead of doing by read, by write, by random, by sequential, and by service time, you could define bucket ranges by any attribute at all. So if you wanted, you could define a set of 100 buckets by LBA range, and then you could see the activity within each 1% of the LBA range across the volume or something like that. If we had an IO sequencer that was playing back a trace of customer IO, we could show if the workload characteristics were different in different areas of the LUN by funneling all of the IO across the LUN to different buckets depending on where in the LUN the I/O was going, etc. As I mentioned, at all the time that you do roll-ups, all of the bucket breakdowns, that array of buckets for read and write, random sequential, and the service time histogram, those are always preserved across all of the roll-ups. So we have detailed roll-ups, random read, random write, sequential read, sequential write. We have the random roll-up, the sequential roll-up, we have the read roll-up, we have the write roll-up, we have the overall roll-up. So these are the categories that you pick from in the source equals workload category parameter. Again, here we can see that you can select category equals overall, read, write, random sequential, and then the 4. And actually, these are virtual categories. If there's a need, we could provide access to the more fine-grained underlying category bucket array with the service time histogram, or we could define other virtual category functions as different aggregations of those buckets too. Okay, so those are the things you can pick from for category. At the fine-grained individual buckets within the array of buckets that goes through the roll-up engine, actually those individual buckets are a set of 3. There's one for bytes transferred, and when an I/O completes, we always post the number of bytes that were transferred into the bytes transferred accumulator. And then we also, for that I/O, post the service time for that I/O into the service time accumulator. And then if IOPS is not equal to max, then we compute the response time and we plug that into the response time accumulator. So these are the 3 types of accumulator you can pick from when you're specifying a focus rollup: bytes transferred, service time, or response time. And the count in bytes transferred or the count in service time is the number of I/Os. So if you're looking for IOPS, you're probably going to want to use the count accessor. If you want to get the service time, then you probably want to use the average accessor. So the summary is, for source equals workload, when you're getting data from IV test host workload threads, the category is one of those virtual roll-up functions to the matrix of the individual accumulators. It's overall, read, write, random sequential, or the 4-way breakdown. Then the accumulator type, it's which of the 3 buckets at the fine-grained level. Is it the bytes transferred bucket, or the service time bucket, or if IOPS is not equal to max, the response time bucket. And then once you're looking at an accessor, you can find out what the average is, how many were poked in, what the min-max was, etc. So that's source equals workload. Then you can also pick source equal RAID subsystem. Subsystem performance data is collected from a command device, and for each subsystem with a command device, there's a subfolder within the test step folder where each CSV file has one line per subinterval within that test step. That's the raw bulk RMLab API data that's collected for every subinterval. So for every existing LDEV machine, whether or not it's participating in the test, you get all of the LDEV metrics once per subinterval. But there's no connection between this and particular roll-up instances. So then there's a small subset of the metrics which are extracted from the bulk subsystem data, and then they're filtered by roll-up instance, and then summarized by roll-up instance. And when we say filtered, what happens is, knowing the configuration of the subsystem and knowing which LUNs and which LDEVs are behind each roll-up instance, we can know which subsystem RMLab API particular resources should be associated with this roll-up instance and therefore accumulated. So for example, if you do a roll-up by MPU, you'll see 4 MP cores reporting for a single MPU in an HM800. So to pick from this table, you have to at the first level, you have to pick which subsystem element, and then within that, which element metric. And the subsystem element that you can pick from today is either MP Core, Clipper, Parity Group, or LDEV. And then there you can see the element metric that's available for those subsystem elements. So in other words, for Clipper, you can only look at write pending percent. For MP Core, you can look at busy percent, and you can also look at I/O buffers. This is something that nobody studied so far, and I'm not really sure what it represents or how meaningful it is, but it shows how much load the MP Core is under in some fashion. For parity groups, you also get busy percent, but you also get that busy percent broken down by random reads, random writes, sequential reads, and sequential writes. Then for LDEVs, you get those things shown: read service time, write service time, and then there's more breakdowns by random. You can see the block size and the random block size, the sequential block size, etc. All those things. So that's what you can pick from right now. If you want to do dynamic feedback control on something else in the subsystem, it's very straightforward. You can just put I can just put the things in the table for you and add more of them. The way this works is via a config filter that's prepared in advance before the subinterval starts. And so what I do is, for each instance within a particular rollup, for that instance, I spin through the workload threads that comprise the rollup instance, and then I look at the attributes of the LUNs associated with those workloads, and then you can see the LDEV. The LDEV may have a pool ID, or it may be an internal parity group, in which case a parity group number, so that you can, directly from what the attributes of the LDEV are, as well as things that you can infer if you're knowledgeable about the subsystem, such as what is always connected to what, and those kinds of mappings. So we can have second or third level indirectly associated with subsystem elements. So what we do in the configuration filter is, for each of the things such as parity group or LDEV or MPU that we're going to be filtering, we post those IDs, those identifiers for parity group, LDEV, or MPU that are associated with this particular rollup instance into the config filter. And then when the subsystem data comes out, it gets filtered for each rollup instance against this config filter. And if the particular instance of the thing is in the filter, then it gets filtered for therefore you can filter by parity group right now, or you can filter by LDEV or MPU, etc.